Hello everyone and thank you for watching. Today I'll be presenting our paper and empirical analysis of test failures in AI-generated pull requests submitted to the MSR 2026 Mining Challenge. My name is Ali Reza and I'll be presenting on behalf of our research team here at Bowling Green State University. With that said, let's dive right into the study. Now, we all know that testing is a fundamental part of the software development lifecycle. However, anybody who has ever written a test as a software developer can agree that manually writing and maintaining these tests is incredibly laborious and often time-consuming. To address this challenge, researchers have proposed numerous automated test generation methods. Early approaches used heuristic and search-based strategies, and later we saw supervised training of transformer models. But most recently, the field has shifted towards using large language models and agentic AI, which offer a more practical approach for test generation. Now, while AI agents have achieved great results, studies still show that they frequently generate tests that fail to compile or execute. Now, we wanted to study how these failures actually manifested in real-world software development scenarios. Thankfully, the AI Dev dataset featured in the Mining Challenge gave us a massive collection of AI-generated pull requests that we could analyze, which led us to two core research questions. One, what are the most common types of failures in AI-generated tests? And two, how do different AI agents compare in terms of failure rates and types? To answer our research questions systematically, we first developed a unified test failure taxonomy. To do this, we reviewed prior studies and divided errors into two main buckets: compile errors, which stop the test from building, and runtime errors, which happen during the execution itself. And as you can see, this gives us 8 distinct categories ranging from basic syntax issues to deeper logic and assertion failures. Now that we had our taxonomy, it was time to set up our study pipeline. We randomly sampled 500 merge pull requests with test failures in them from the dataset. We specifically gathered 100 pull requests for each of the 5 agents featured in the dataset. We were able to automatically identify test failures by parsing CI logs and checking their status codes. Next, 2 of our authors independently annotated each failure using the taxonomy mentioned earlier. Any disagreements in the labels were resolved through discussions with a third senior author to ensure an unbiased classification. Moving on to our findings, starting with RQ1, which was what are the most common failures. Well, the data clearly shows that the runtime errors are more frequent with over 62% of all failures. The most common defect, however, was assertion failures, followed by runtime crashes and import errors. Well, this tells us that modern AI agents are actually quite good at writing tests that are syntactically correct, but they're struggling with understanding the logic of the code they are actually testing. When comparing different agents for RQ2, we found that Copilot, Claude Code, and Devin were very runtime dominant, which means they generated compilable code but failed during the execution. For instance, Copilot had the highest runtime crash rate out of all the models. Furthermore, OpenAI Codex was compile dominant and mostly failed because it didn't understand project dependencies. And finally, Cursor was the most balanced model, but it performed poorly when interfacing with build configuration tools. So what do these results actually mean for project maintainers and software developers? Well, the high rate of assertions we observed is concerning because bad assertions can create a false sense of security in the production tests. We also saw that the bottleneck has officially shifted from teaching AI how to write code to teaching AI what the code is actually supposed to do. Now, based on all of these findings, we believe the future work should focus on improving AI semantic reasoning and giving the agents better context of the overall project. Also, since each model actually excels in a specific aspect of software engineering, another direction we could go is multi-agent systems and pipelines, specifically for software testing. That concludes our presentation. Thank you for your time and attention.